Good. So it's a pleasure today to have Surjeet Rajendran and David Kaplan from Johns Hopkins University. They are a couple of physicists who have been doing very interesting work, definitely off the beaten path, very interesting ideas. And today they are going to tell us about their ideas on how to modify what we take for granted as the usual collapse of black holes, and maybe resolve the firewall paradox that some of you may have heard about.
All right, so thank you very much for giving us the opportunity to speak. It's fun to talk physics with a large number of people. So the way we're going to do this is basically in the first half of this talk, which I'll be giving, I'm going to describe two problems in black holes. One is the well-known black hole information problem. I'll give you our view on what it might take to solve that. And we actually believe that the solution to this problem is likely closely tied to another problem that exists in black hole geometries. This is the so-called Cauchy horizon problem in Reisner-Nordstrom and Kerr geometries. The latter problem is much less popular. It's not as widely known to many people, but it is nevertheless a very interesting problem. And we think the kinds of structures that you need to know to tackle the second problem, for which people have ideas on how to do, could easily be applied for the black hole information problem as well. So I'll first start off by giving you an overall introduction into where these problems come from, more from an intuitive picture rather than anything particularly mathematical that way. Okay? So what are black holes and why do we think about them? Well, if you take a large enough mass and you put that in a small enough region, general relativity predicts that the force of gravity becomes so strong that the object will collapse and form a black hole. A gravitational collapse occurs. And in general relativity, there is a solution that describes this particular collapsed object, and that is the Schwarzschild metric that describes the exterior of this particular object. And it is given like so, as you have seen many times, with 1 minus rs over r dt squared and so on and so forth. And in GR, you can prove that this is actually the unique spherically symmetric vacuum solution. There's a theorem that guarantees this. Okay? The Schwarzschild metric has an interesting point, which is the event horizon at the point r equal to rs, where the usual story is that nothing can escape, because once you're inside the event horizon, the force of gravity is so strong that you can't leave that region. Now, here comes an interesting question. Right? So it is often the case that when we talk about physics to our students, we lie. We often claim something is spherically symmetric in order to solve the problem. When we look at the Earth's gravity, we write that as a spherically symmetric solution. And you might ask the same question here. Is somehow this black hole solution in some sense the spherical cow approximation, that I'm only doing this as an approximation even though in reality it's not actually true? And it is a good question because, after all, the collapsing object that went on to form the black hole had a whole bunch of multiple moments. So you might naively expect that the collapsed object should also have all these multiple moments outside. And many of you have undoubtedly heard of the so-called no-hair theorems, which probably tell you that this is not the case, that somehow this spherical cow approximation is really true. And in the next couple of slides, I will give you an intuitive understanding for why the no-hair theorems are actually true. So let us perform a thought experiment. I'm just going to draw this not in the usual Penrose diagram, but just as intuitive diagrams of how we think about black holes. So I'm going to have a black hole that has the event horizon at the r equal to rs, some region. And I'm going to have two observers, Alice and Bob. You know, in this game, if you want to sound like a deep person, you have to use the word Alice and Bob. So there'll be two observers, Alice and Bob. And Alice is standing outside and Bob is going to fall in. Okay. Now, Bob carries with Bob an electric dipole in their hand, and Alice has an electric field sensor. Okay, that's it. And Bob is going to communicate to Alice by flipping that dipole back and forth. So just by measuring the classical electromagnetic field, Alice can get information from Bob, right? Whether the field is up or down, is sending you a bit of information. So far, so good. And now Bob, who's outside and is happily communicating with Alice, jumps into the black hole. And the question is, what happens to the dipole field of the dipole that Bob has in Bob's hand as Bob crosses the horizon? Is this dipole field visible outside? Of course, the main point is that in the conventional picture of the black hole, the horizon is an empty part of space. There's nothing there, right? You just fall right through unbroken. You just jump right through the horizon. And so there's nothing at the horizon to record the value of the dipole as you cross the horizon. Moreover, in the conventional picture, it is also the case that nothing happens to Bob or the dipole. So Bob will happily jump inside and go inside the horizon and can continue flipping the dipole back and forth. Nothing has stopped Bob from doing this. But if the flipped dipole fields are still visible outside, it becomes a way for Bob to communicate with Alice, right? So if the dipole field of Bob is visible outside after Bob has crossed the horizon to Alice, you are now able to communicate across the event horizon, and that violates causality. So somehow this must not happen. Somehow the equations of motion of general relativity must be that something prevents this from actually happening. So could it be the case that for whatever reason, the laws of physics are such that the moment Bob crosses the horizon, all electromagnetic fields must vanish outside? Could that be what happens? All fields go to zero. That, however, has a problem, which is that Bob can fall inside with a net charge. And then you can ask if the monopole field should also vanish when Bob has crossed into the horizon. That, of course, can't be true, because if that was true, you would violate Gauss's law. You violated the conservation of charge, right? So the question before you is, how can I preserve causality as well as at the same time preserve conservation of electric charge? What should the field equations do in order to preserve both of these two important elements of physics? There is a way to do that, which is that to preserve causality and Gauss's law, if somehow it is the case that the laws of physics are such that the equations of motion give you a solution where only the monopole field is somehow non-zero outside, but the rest becomes zero, right? Suppose that is the case, that when you cross this horizon, the equations of motion work in such a manner that the monopole field is preserved outside, but the rest go to zero. If that happens to be the case, notice that you can preserve Gauss's law, because the monopole field is really what's important for Gauss's law, and therefore that is non-zero, so Gauss's law is preserved. At the same time, you cannot use the monopole field to communicate with anyone outside, because the monopole field is tied to a conserved quantity. So Bob is unable to change the monopole field in any significant way, and therefore cannot actually communicate outside. Thus, to preserve causality and Gauss's law, it must be the case that the laws of physics preserve the monopole field, but the rest becomes zero, right? That's the only consistent way of handling these two twin challenges. And indeed, this is what the no-hair theorem show. I've just given you an intuitive reason for why they're correct. To see it correctly, you want to do the math. And the math does, of course, work out and show that this is the case. So you realize that the metric is now solely described by conserved quantities, right? And that is the only thing that the exterior observer can see in order to preserve causality and these conservation laws. This, of course, leads to a vast simplification, because the incoming object that actually formed the black hole is not just described by its conserved quantities. It's got an enormous number of moments. A star would have 10 to the 57 moments if it's one solar mass. But all of that complication disappears, and the exterior metric is just described by a small number of parameters. Now, if this was all there was in the world, everything would be fine. You know, there's nothing classical about this. There's nothing in classical mechanics that would cause any kind of trouble at all. So this could have certainly been the way the world works, and we would all been very happy. But there's one thing about the classical problem that makes you a little bit unhappy, which is the fact that if you look at the event horizon, something interesting is in fact happening, right? For example, the time coordinate here changes sign. The space coordinate here changes sign as you cross the event horizon. Plus, it is also the case that the event horizon, there seems to be a singularity there, a coordinate singularity at least, because some terms are going to zero. So it looks like the metric is ill-defined at the point r equal to rs. But you can do the following exercise. Anytime you see some coordinate singularity in your space, you can ask if there is actually the geometry itself behaving badly. For example, in spherical coordinates, the point r equal to 0 is poorly defined, but nothing interesting is going on there. You can just change coordinates and remove it. So if you look at this particular geometry and you compute the curvature invariance, such as the Ricci scalar or Riemann squared, these kinds of quantities, you will find that all these curvature invariants, the things that you normally use to diagnose a geometric problem, they're all finite. And thus, this thing looks a lot like a coordinate singularity, and thus it suggests that you should be able to change coordinates to remove the singularity at the point r equal to rs. Then comes the question, what can these new magical coordinates look like that remove this coordinate singularity at the point r equal to rs? And here you run into the problem, which is that there is the famous thing called the Birkhoff theorem, which essentially shows that the Schwarzschild metric is the unique time-independent solution. Okay, so if you try to time-independent spherically symmetric solution. So when you try to prove Birkhoff theorem, okay, if you go to the math, you will essentially find that if you try to write the metric in a time-independent way, you will derive the Schwarzschild solution as a consequence. So there is no freedom for you. The moment you require time independence, the Schwarzschild solution automatically flows out of it. And thus, if I want to come up with a new set of coordinates that remove the coordinate singularity, I have no option but to give up on the time independence part of it, because time independence forces me to Schwarzschild. Thus, whatever new coordinate I'm coming up with has to depend upon time. So what? Okay, but this is where, because the world is quantum mechanical, things get more interesting, which is that I now have a new set of coordinates which are no longer have a coordinate singularity at the point r equal to rs. That was my goal. But in order to do that, I had to write a time-dependent metric. So once you have time dependence and the world is quantum mechanical, interesting things can happen. And we can try to understand how quantum fields behave in this time-dependent geometry through just some simple particle in a box style arguments. So I take a box and I'm going to vary its size. And I'm interested in how oscillators of different kinds behave in this particular case. So there are two kinds of modes you can be interested in. A high frequency mode, high frequency relative to the rate at which I change the box. So if I have a high frequency mode and the box is changing slowly compared to the frequency, then of course the evolution of this mode is given by adiabaticity. And so we would say that a high frequency mode, if it's a vacuum state in one box, it goes to the vacuum state in the other box. That is the adiabatic evolution. On the other hand, if I have a low frequency mode, low frequency compared to the rate at which I'm changing the box, then of course that mode undergoes sudden evolution, which means that mode will get excited as I go to the larger state of the box. And thus what we've realized is that the moment I have this time-dependent geometry, and since there's a quantum fields of various kinds of various energies, there will be some quantum fields that will get excited because they are these low frequency modes. And that means you must have particle production happening in the system. And since the only scale in this problem is the Schwarzschild horizon, this horizon would radiate at basically 1 over Rs, and that is the temperature naively at which it comes out, right? So what we have now seen is that if you look at the standard black hole geometry and you want to remove the coordinate singularity, you are forced into a time-dependent solution. And the moment you have time dependence, you must have radiation. And thus this black hole cannot remain quiet anymore. It must be radiating particles. As it radiates particles, it will lose energy and mass and eventually disappear. And that is Hawking evaporation. This gives rise to a problem, that is the so-called black hole information problem, which is the fact that the black hole that was formed from regular objects like you and me, right? We have all these bells and whistles and shapes and all these things. And there's all kinds of information content in them. When all of these guys hit each other and they're going to collapse, they become this nice Schwarzschild geometry. That's what the no-hair theorem showed. And that means there's absolutely no information about any of these multiples outside. It's all completely zero, right? All of these complicated things have become a nice spherical point. And that becomes the no-hair situation. Now, the key point is that everything about the radiation is happening outside, right? The radiation is going on the outside. It, of course, knows only about the exterior geometry because that's all it has access to. And in this particular situation, whatever went inside the black hole is unable to communicate with anything going on the outside because, of course, once you cross the horizon, it's a one-way street, right? Anything in the interior cannot talk to anything in the exterior. The force of gravity is too strong to prevent anything from inside ever going outside. So the question is, the radiation is happening outside. It causes the entire black hole to disappear, but all of your information is living in the interior. And how can this information ever be seen outside? Because this is a one-way street. I can't go from here to here. And in quantum mechanics, this gives rise to the violation of unitarity, because if this was all that was happening, it would be the case that a variety of initial states would have all become the same final state, and that just violates unitary evolution. Okay. So let me put this in a more conventional picture that people are probably more used to, or at least the GR community. This is the Penrose diagram, okay, of this whole story. And here is the Schwarzschild metric that we talked about. And I've shown this in what are called Kruskal coordinates. This is the coordinate change I talked about, where you have removed this, the coordinate singularity at r equal to rs at the expense of having a time-dependent metric. Okay, so this is capital T is time and capital R is space, and they're related to little t and small r in more complicated ways. So in this particular geometry, if you're an observer who was at a fixed r equal to r naught, small r equal to r naught, you are what would be considered an accelerated observer, as you should be, because you are a guy sitting at rest outside a gravitational system. So you have a rocket that's holding you up. So you are an accelerated observer, you're doing that. The event horizon itself is a null line, okay? Light lives at the event horizon, as light should live in the event horizon. Only light can go over there, and that is the point r equal rs, if you will. And now one can ask, what happens to an observer who's freely falling into this thing? So when the observer is outside the horizon, this is a regular observer, he can move back and forth in small r, just like you and me can move back and forth in small r. As you cross the, as you cross the horizon, something interesting happens, which is that if you look at this particular geometry here, roughly speaking, the time and the space coordinates change sign. So what used to be time acts like space, and what used to be space acts like time. And the point r equal to 0, therefore, is now a point in your future. Okay, that is one way of talking about it. That's a perfectly sensible way of talking about it. But a more simpler way of saying this is just the fact that the force of gravity inside is so strong that you have no option but to continue falling. Nothing can hold you back. So you have no option but to continue falling. And therefore, the singularity at the point r equal to 0 can be thought of as a point in your future, since every equation of motion you write down will require you to continue falling. Okay, so that's all it really is. And in this picture, the information problem is the fact that the Hawking radiation is happening outside the horizon, and my singularity is living in here. The singularity is formally a point in my future, so it's unable to talk to anything over here, or in other words, I can't send signals from here to here. Okay, so since the singularity is unable to communicate to me, how do I communicate? What's going to happen? So the key question, therefore, becomes, how do we get information from the interior to the exterior of the black hole? How can that be possible? Now, we're going to take a very physical point of view, right? You may come up with all kinds of fancy schmancy things, but at the end of the day, if you have to get information from the point r equal to 0 to the exterior, something has to propagate. Unless something actually gets out of there, you are not going to carry information away. And this is perhaps our slogan, if you will, for what motivated much of our work, is that no information without propagation. Unless something moves, you are not getting information out. Now, whether you like it or not, when something actually goes from the point r equal to 0 over here, something actually propagates, you will violate general relativity. That's just true, because in GR that can't happen. So the key question is, how can we sensibly violate general relativity, right? So I'm going to confess that in this talk, we will violate general relativity. So I will commit that crime. So what Dave and I are hoping for is that we want to commit this crime in such a manner that we cannot be prosecuted for it. Okay, so that is exactly what we are going for. And there is a sensible way of doing this because, of course, general relativity is just an effective field theory. So it should be possible for us to sensibly violate effective field theories. Well, how can that be possible, right? So to propagate from the singularity to the horizon, I, of course, need a large correction to the metric. As long as the GR metric is correct, this is not going to happen. So let's think about how we can modify that. So let's take a scalar field phi that I want to move from the horizon, from the singularity to the horizon. Okay, how can I make the scalar field do all these crazy things that I want to make it do? Well, let's look at the scalar field action. It couples to the typical GR metric. If that is all there is, then of course I can't do what I want. But in general, of course, there will be higher dimension operators that couple to the scalar field. And since this is actually what the scalar field knows about, effectively the scalar field will move as given by the causal structure of this metric. It doesn't just see G mu nu, it of course sees higher order corrections as well, right? So this field phi will move as per this effective metric. Pardon me for a second. But to change the causal properties of G mu nu, I would require these higher order terms to be as big as m Planck squared in order to make an order 1 change for this scalar field to actually get out, right? These terms have to be large for this to actually work, and they have to be large all the way to the horizon. Otherwise, I can't do what I want to do. This, of course, is not true in the Schwarzschild geometry, because in the Schwarzschild geometry, these terms are large only at the point r equal to 0. Everywhere else, they're super tiny. So this seems like it's not going to happen. Okay. And you might then ask, well, why do I believe that the Schwarzschild geometry describes the interior of the black hole, right? Because if the Schwarzschild geometry is true, only at r equal to 0 are these terms large. So you might very reasonably ask, well, perhaps the interior geometry could be very different. Why should I believe in Schwarzschild? Well, you have good reasons to believe in Schwarzschild, because in the Schwarzschild geometry, there's only a coordinate singularity at the horizon. There is thus low curvature all the way to the, at the horizon, the Ricci tensor, etc., is super tiny. So you would say, as an effective field theorist, general relativity should hold at the horizon because these terms are small. Okay. Moreover, you can put more of a quantitative picture to this, where you would say, suppose, look, you crazy guy, let me allow you to change the, Riemann in some big way in the interior. But look, I have another quantitative problem. If it's really the case that Riemann and all these things are Planckian all the way to the horizon, so I really have something like that would imply basically that I have local mass densities that are Planck to the 4th. It's really required, right? To get Riemann at m Planck squared all the way to the horizon, the local mass density better be Planck to the 4th. And let me now do a naive calculation of the overall mass of the black hole, which would then be m Planck to the 4th, the local density times the volume, which is presumably Rs cubed. Let me do that calculation. That gives me a total mass of the object, that is m Planck to the 4th times Rs cubed. That is m cubed over m Planck squared, which is way bigger than the mass of the black hole, right? So this whole art thing just seems like hopeless. How could I possibly go from r equal to 0 to the outside by violating general relativity all the way through? Because look, first of all, this is not true in Schwarzschild. It has to be the case that Schwarzschild should hold, because I have low curvature everywhere, okay? So I have no reason to think effective field theory should break down. And even if I gave you all of that, the overall mass of the black hole is way off. So this just seems completely hopeless, and one should therefore give up, okay? Seems hopeless. That's what I used to think too, actually, by the way. So if I had given this talk to myself 3 years ago, I would have said, oh, you're crazy, go away. But then we learned about another problem that is extremely interesting, where all these facts will turn out to be wrong. And that's what motivates a bunch of our work. And that is the problem of what is called the Cauchy problem, or the inner horizon problem in Reisner-Nordström and Kerr geometries. Okay, so Reisner-Nordström describes charged black holes. Kerr black holes describe, rotating black holes. There may not be very many charged black holes in our universe, but Kerr black holes are very real. They're in our universe. And everything I say today will be true for Reisner-Nordström and Kerr black holes, although I will only focus on the Reisner-Nordström story, because that's where we're able to calculate something because of spherical symmetry. So both of these geometries are described by metrics where there are two horizons. There's an inner and an outer horizon, basically places where these terms vanish, f of r vanish. In Schwarzschild, you only had r minus rs. Here you have r minus r1 and r minus r2. And here is the interesting fact. For a large black hole with a large charge or a large angular momentum, the latter category exists in our world, both the inner and the outer horizon exist in regions of low curvature. Okay, so if you are an effective field theorist, you should say these things exist in regions of low curvature, therefore I must trust general relativity both at the inner horizon and the outer horizon. That's what you should say as an effective field theorist. So let's take these things at face value and let's see what happens to an observer who jumps into this black hole. Once again, I'll just draw a normal person diagram and not worry about a Penrose diagram, but the physical things I'm telling you will be true in both cases, of course. So here is my Horizon-Nordstrom geometry. I have R equal to R2 is an outer horizon, R equal to R1 is an inner horizon. And I have an observer who is outside who's going to jump in. Okay. Outside, of course, it's like regular space. You can move back and forth in space. And f of r, of course, is nice and positive, right? So this is very regular. So this observer jumps into the black hole. As they jump into the black hole, they cross the point r equal to r2. When they cross the point r equal to r2, that is the outer horizon, f of r now becomes negative, as you can see from this equation. So this is just like jumping into the regular Schwarzschild black hole. When you're inside over here, right, the force of gravity is so strong, time and space have changed meaning, so you have no option but to continue falling towards the inner horizon. This is just your standard view of the black hole, right? So once you cross this region, you have no option but to continue falling. You will fall and you will cross the point r equal to r1 because that's your point in your future. That's what you normally say. But once you're inside the point r equal to r1, notice that f of r has changed sign. And when f of r has changed sign, time becomes time and space becomes space. They become normal again. And in particular, the point r equal to 0 is now a point in space. It's no longer a point in time, right? It's just a point in space. And thus you can jump and hang out over there. Okay, you're not inevitably required to fall in there. And mind you, once again, because for a large black hole, these are at regions of low curvature, if you believe GR and if you believe GR applies in regions of low curvature, you would say if I cross this region and I come inside this black hole, I can happily spend my life all the way in here, right? I can safely avoid the coronavirus and all that crap and be happy in here, nice and secluded. It's a good way to be. That's what GR naively predicts. Not only that, you can get more ambitious and you can say, I'm going to try to leave this region because what's going to block me, right? Gravity is nice and weak here. I should be able to try to leave this region. The question is, if you try to leave this region, where can you go, right? You can't go back to where you came from because that would require you to go back in time. It requires you to go back from R1 to R2, and that means moving back in time. So that's not possible. So you can't go back. Nor can you just stop there because just stopping there is a violation of the rules of geometry, right? I have the space-time curve. That curve is not hit a singularity. So where do I go? Okay. I have to extend it somewhere. And this is basically where the GR books will say something that is totally ridiculous and nonsense, which is that they will basically say that the only way you can extend this curve is now extended to a different universe. Okay, so that is the standard textbook answer, okay, at least one standard textbook answer, which is that you jump into a curved black hole, you cross the outer horizon, nothing happens to you, you cross the inner horizon, nothing happens to you, and then you try to leave that region, you're going to go into a different universe. So you got to ask yourself if you believe that, because curved black holes are real in our world. Do you believe you jump into them, you're going to go into a different universe? Now, you might even take a very liberal attitude and say, look, GR can create universes that will, so who am I, you know, some random dude on the planet Earth to say I can't go into different universes? Maybe that happens. Okay, maybe that happens. But that still creates a new problem for you, which is that GR does not tell you which universe you will go into. It doesn't tell you where I am patching myself up in, right? I'm just ending up in some random universe, and formally that random universe has its own boundary conditions. So what this has now caused is that this has led to a situation where GR has failed to be a predictive theory, because given initial conditions of in one universe, I form this black hole, I jump inside, I end up in a random universe, and I can't predict what happens in there. So I've got a failure of predictivity, which means GR has failed to solve the Cauchy horizon problem. Cauchy problem. I cannot give you initial conditions and predict what happens. And that, of course, is a very serious problem, right? It's a serious classical problem that appears the moment this kind of black hole actually ever exists. So if you think about this problem for a second, you almost immediately realize that the only way to solve this is for there to be a large change to the metric. Okay, something dramatic has to happen so that there is no inner horizon at all. Somehow it has to be the case that even though general relativity predicts that this is what should happen, something must dramatically change the story here so that there is no inner horizon. And in particular, if you think about what can the possible end state be for a static black hole, the only real possibility is that there should be a gravitational singularity. And by singularity, I mean in place where GR breaks down at the inner horizon, right? That is the only possibility. Everything else gives rise to something totally crazy, okay? And unlike the black hole information problem where you could have mumbled about, you know, quantum mechanics, whatever, entropy, blah, blah, Here, whatever happens needs to be a fast classical effect, because the moment the black hole is formed, something needs to happen, a singularity needs to happen at the inner horizon. How can that happen? People have thought about this before, both Penrose as well as Israel and Poisson and a number of other people, and there is an accepted story here. And we're going to make use of those lessons for what we need for the black hole information problem as well. So here is the standard story, okay? Imagine I have an observer who sits right inside the inner horizon, and I am watching some starlight or some perturbation or whatever falling from far away. Far away, that perturbation has an energy E infinity, okay, that's what it is. And I'm standing inside and I'm measuring that energy, and that energy is ER1. So as this falls in, you can show that there is a dramatic blue shift of this energy from far away. Okay, it blue shifts as R1 divided by R minus R1. And formally, as you approach the point R equal to R1, this diverges. Okay, so what this gives rise to is a very interesting point, which is that there is a significant possibility of a significant local energy density that's falling in, building up, without changing much of the external mass. So I only took in a tiny amount of mass far away. As it fell inside, it got dramatically blue shifted. So if I'm interested in local things like GR breaking down, etc., I only care about the local mass, and I can possibly get a large local mass here without changing the mass outside very far away. Okay, but something about this should make you a little bit nervous, where you're like, is it really the case that external perturbations are what is necessary to save something like causality, right? Something about the Cauchy horizon problem. After all, if I take a solar mass black hole, do I really expect a tiny photon from far away coming in and dramatically changing its geometry? So we can quantify this a little bit better, where we would say, look, there are actually no infinities in physics, right? We know that when there's an infinity, the theory is broken down. So a very reasonable thing for me to do is to say that I don't actually know how particles are moving at a sub-Planckian length. So what I'm going to really do is I'm going to regulate that divergence at the Planck length. I don't know what's going on in sub-Planckian length, which then of course means that if I have a finite energy falling in from outside, I will of course get a finite energy inside, right? Because infinity is now gone, though it can be amplified. So we can just do that. We're going to cut that divergence off at the Planck length. So if I throw something off at energy E infinity outside, when it appears in over here, it's going to appear as E infinity times M Planck R1, okay? And if you take that the inner horizon is about as big as the outer horizon or whatever, you realize that the amplification is a large amplification by a factor M over M Planck times E infinity. Okay. So now let's do something more quantitative. Now we say, look, I want to actually have a singular, by which I mean a Planck density object at the inner horizon. Let's call it a Planck density shell, which means it has energy density M Planck cubed. It's now over a surface area R1 squared. And if I compute the overall mass that should be in there, okay, to form this object that I want, the local mass must be M squared over M Planck. That's what I need in order to create this big difference. And that means the amount of energy that has to fall in from the outside should also be comparable to the mass of the black hole. Which makes, sense, right? That if I want to change something dramatic about the interior in some crazy way, probably it is the case that the amount of mass that fell in should be comparable to the overall mass that fell in the beginning. That makes physical sense to me. So this makes you a little skeptical about the external perturbations picture. Moreover, nowadays there is even a more mathematical objection by Peter Heinz and company. And they observe that if you actually lived in a de Sitter world, okay, there's a positive cosmological constant, I can now think about a Reisen and Nordstrom black hole whose charge and mass are large enough that the inner and the outer horizons are comparable to the cosmological horizon, because I have a lambda now. In that case, when something from outside falls in, the gravitational blue shift that you're getting from the infall can be counterbalanced by the redshift in the de Sitter universe. And you can basically show that the two of them basically cancel and they soften this divergence. So do you really believe, if you believe in external perturbations coming in, do you really believe that something that should be essentially, irrelevant, like a positive cosmological constant, should change something with the predictivity of general relativity? So this thing really seems a little bit funny. Is it really external perturbations? But then you should ask, why are we focused on external perturbations? What is the magic of external perturbations really in the story, right? Because why do we get these blue shifts? These blue shifts happen because gravity is attractive. When I'm well outside and I'm falling in, gravity is attractive, I keep falling in. I cross the outer horizon, gravity continues being attractive, and that's why my particles get more and more blue shifted. But notice that when I'm inside the inner horizon, gravity becomes gravitationally repulsive, okay? This is a fact about these geometries. In the Rice-Nordstrom case, this happens because the electromagnetic field has energy density that behaves like a cosmological constant, pushing you outward. In the Kerr geometry, this is because the singularity is spinning. When it's spinning, there are centrifugal forces or vorticity that pushes you outward as well. So gravity is gravitationally repulsive inside the inner horizon. And that in a sense is why these horizons exist. Because here you can't fight off gravity, but here gravity fights itself off. And thus you're able to hang out over there, right? That's why things become more normal. But that suggests something interesting, right? Just like how I had a large blue shift on this side, it's also very reasonable that I can take my mass on this side and move it around and get these large blue shifts as well, right? Like nothing about all that mattered about the interior are the repulsive natures of gravity. And gravity is nicely repulsive in there. And so you must also get a blue shift when things go from here to here. So you should really ask, right? Is it not reasonable that I can push mass and charge from the singularity to the inner horizon? And that becomes a new way for me to create a large energy density in there, okay? And once again, this blue shift should lead to a large local mass that appears in there without changing any of the external parameters. That should clearly be possible, right? Intuitively, it sounds like that should be possible. And that's where our story really begins when Dave will talk about it. We will say, suppose it's really the case that there is an inner horizon that exists at the Rice-Nordstrom, that there's actually a singularity at the inner horizon. How can that happen solely from internal parameters without relying on something external? And my God, if that was true, right, could the same kind of thing also apply to the Schwarzschild geometry? Because notice that all of the objections that I had for my story for the Schwarzschild geometry also apply to the inner horizon of Rice-Nordstrom. First of all, in the Schwarzschild geometry, I wanted to believe in the GR story because curvatures were small. That's also true here. The inner horizon naively has small curvatures. Secondly, I also said that to change the Schwarzschild geometry dramatically, I needed to have an enormous amount of mass. And this enormous amount of mass had to exist without changing my external parameters. Notice that is also true for the inner horizon of Rice-Nordstrom, because indeed the local mass is enormous because it's at Planck density, right? But apparently it is the case that if I have to preserve predictivity of general relativity, these objections are not valid in the inner horizon. And we are asking, could the same thing be true for the outer horizon as well? And so I would say in some sense that what we're going to now discuss with David is in many ways pretty conservative, right? We are taking a structure that everybody in the world believes about the inner horizon of Rice-Nordstrom and Kerr, that if you, for example, look at Sagittarius A star, right, the black hole in the center of the galaxy, I had always thought that the singularity would have been living in a tiny Planck region, but that makes no sense. That singularity has to be stretched almost all the way to the horizon. It has to exist at the inner horizon for sure, right? Like solar system size has to be true. So could we now go past that to the outer horizon itself? Because if we did that, we can solve the black hole information problem. So that's where I will stop. And this is the outline for the rest of David's talk, which he will give. So I will stop sharing my screen. And I don't know how you guys do questions, but if there are questions, I'm happy to answer them and all that.
Yeah, are there questions for Surjeet? Otherwise, we can postpone everything at the end.
A good time to have questions now, if somebody has.
I have a quick question. So is this related to the fuzzball proposal?
No, it is not. Okay, so the crucial difference between us and the fuzzball is that in fact, Dave will discuss this, right? So there are many ways in which you can write what are called black hole mimickers, which are essentially something that has the Schwarzschild solution on the outside, but a different interior. There are many such solutions. The fuzzball is one of them. The crucial question to all of this is formation. How do you take regular matter like you and me, put a whole bunch of us together, it'll collapse to form a black hole. How does that collapsing object become whatever you want it to be? And we would say that the solution that we proposed, well, in a sense, basically for anything that is collapsed to go outside and become something else, you would have to violate general relativity. Otherwise, you cannot do this. And we would say that the only way to violate general relativity is through Planck density objects like what we are talking about. The fuzzball is a low density solution. And thus, initial conditions, I don't see how a generic collapsing condition will become a fuzzball, while in our case, we would argue that it's plausible. Although since it breaks GR, we cannot actually show it, but it is plausible. That's all.
I'll discuss it. I'll bring it up. It'll come up again at the end.
Yeah.
There is a question by Paolo Pani in the chat.
Yes.
Yeah, I looked at the question. Maybe let's do the second half of the talk because it will be relevant then. But I think the question is essentially that he's describing Reister-Nordstrom in the eternal version of a black hole. How does the interior change during the collapse? And the whole issue is the fact that when you're collapsing, because you're at low curvatures, you expect general relativity to describe in detail what the interior should look like. So you still end up with an inner horizon problem in that case, and a Cauchy horizon. But it'll come up again in this talk, so.
Okay.
Yes, so here's an outline. Basically, I'm just going to give static solutions in GR, argue that it's useful to do these static solutions, and then talk about how in the big picture we might expect real black holes to look like this. And the warm-up is the inner horizon of Reister-Nordstrom. So Surjeet said that there is an issue with the Cauchy horizon in charged black holes and Kerr black holes. Charged black holes are easier because they're spherically symmetric. And so can we propose an actual physical surface there and solve the equations of GR? And then asymptotically take the density of the surface to the Planck scale. So the way you would see it is we have, hold on a sec. Sorry, I just want to be able to see my own screen. Okay. So the way we'll build it is by taking a surface and asymptotically bringing it to the inner horizon of the black hole. So the outside geometry will be a charged black hole, and there will be a surface that we'll place inside the inner geometry. Now the surface itself could carry charge, and there will be a singularity at the center which carries charge, but the net charge will be the charge of the exterior black hole. There'll be some outer geometry which is Reister-Nordstrom, and we're going to take the thin shell and slowly move it and replace the inner horizon. And we can ask and see if this shell can be of Planck density. Remember the issue with a Planck density shell that the mass could be much bigger than the mass of the black hole, but will that mass inflation or blue shifting at the inner horizon help us? The inner geometry will also be Reister-Nordstrom. It's spherically symmetric. Gauss's law still works even in GR, and the interior charge, the charge of the singularity, will dictate, and the mass, will dictate the metric just outside of that singular point, and we will have that metric. That metric will also be Reister-Nordstrom. And the Reister-Nordstrom of the interior part would also have an inner horizon, but we're going to make that inner horizon large. Big charge and big mass will put that inner horizon well outside of the shell, which means it's not a physical horizon. It's just an indicator of the metric of the inside. But the metric from the inner to the outer changes at the shell. So the only horizon in this case is the inner horizon of what we see from the outside, the Reister-Nordstrom black hole. And we're going to match it to another Reister-Nordstrom on the inside. And to do it, this is GR, it's just differential equations. We will use matching conditions in the differential equation. These are called the Israel junction conditions. And this is a well-known old procedure. And so when we match, we can ask then questions about the shell itself. In order to match these two, can the shell have positive density? Can it be reasonable? Can it satisfy things like the null energy condition? Can the density be bigger or as big as the pressure? Those kinds of questions. So we can ask those questions once we've done the mathematical matching. And so the way you do it is you choose a metric outside and a metric inside, and both of these are Reister-Nordstrom metrics. And so we in order to use global coordinates for time, for example, we have to rescale the time on the inside by a constant, but it's a sort of trivial rescaling. And both of these metrics, as you saw with the Schwarzschild metric or the Reisner-Nordstrom that Surjeet showed, are the standard metrics, and all we have to do is match them at the surface. The surface will be at r shell, the radius of the shell, and we're going to parameterize that as 1 minus epsilon times the inner horizon. And as epsilon goes to 0, the shell approaches the inner horizon. And in that limit, we can ask questions about the density of the shell and the pressure on the shell and even the charge. If you take that limit and you compute using the Israel matching conditions, the density and the pressure, the density runs to a constant. It is a function of the inner and outer horizon parameters of the two metrics. So I could have written this in terms of the charge of the inside and the outside. It's more efficient, it turns out, to write it in terms of R1, R2 for the interior metric and R1, R2 for the exterior metric. Those are the two horizons that you get from Reisner-Nordstrom. The density in the limit where the shell goes to the inner horizon is a constant, but the pressure diverges as 1 over the square root of epsilon. So we, again, are going to cut off divergences, meaning we're going to put the shell a physical distance about Planck length away from the inner horizon, and thereby, once you get to that cutoff, you no longer believe there exists an inner horizon. And so we want to choose a physical distance away from the inner horizon, which is a Planck length. To get a physical distance, we need to use the exterior metric to determine what epsilon is. And it turns out for a Planck physical distance, for epsilon is required to be this formula. R2 minus R1 for the outer metric over m Planck squared R1 cubed. At that scale, at the physical distance of a Planck length away from the inner horizon, you can calculate the pressure, and you get minus m Planck cubed. It's a 2 plus 1 dimensional, it's a hypersurface, so pressure and density are mass cubed. And so you have got a pressure which is Planckian, and it's negative pressure. Now, we don't want the pressure to be much bigger than the density. We would like the pressure and density to at least be equal. This would allow us to satisfy things like the null energy condition or dominant energy condition. The material would be something reasonable, like a solid or a perfect fluid. And we can get there by choosing the other remaining parameters, R1 and R2 of the interior metric. That's just choosing the charge and the mass of the interior singularity. And when we do that, we get a density which is Planckian as well. And now we have what appears to be some sort of sensible material. If it's a perfect fluid, you'd say W is bigger than -1, though the pressure is negative. Now we can ask, what are the physical characteristics of this matter? By setting the shell right at the inner horizon, a Planck length away, we can ask what the interior of the black hole or the interior of this object looks like inside of the shell. If you calculate the physical distance between the shell and the singularity, even though coordinate-wise this seems to be a long distance, it turns out that the physical distance between the shell and r equals 0 is also a Planck length. And that the curvature inside, namely curvature and variance, say Riemann squared, are of order Planckian. They're all, whatever the dimension is, in Planck units, order 1 or greater as you go to r equals 0. So what has occurred now is we've taken this shell and we've moved it to the inner horizon within a Planck length. The density is Planckian, the pressure is Planckian, and it turns out that the geometry inside is also Planckian, and that the radial distance, which looked like a macroscopic distance, has become a Planck length. So the inside in this limit has approached something that violates general relativity throughout the interior. And we trust these solutions because we're starting in non-singular regions at sub-Planckian energy densities. So this really is a plausibility argument that as you get to Planckian densities, we are tracking solutions which exist in GR. And yet something very interesting is happening to the interior. We're losing the volume for what looks like an area. The shell is very massive locally, but the important things are that the shell itself has positive energy density. It's made of a positive mass material, and that while the mass locally is very large, the asymptotic or so-called ADM mass of the black hole is the same. This is just by virtue of we're in GR and the metric is what it is for the exterior. You can check the charge of the shell needed for this to work. The charge of the shell in units of charge per unit mass is greater than or order 1. There's a 1 over square root of alpha in there that takes us above 1. So it's somewhat bigger than 1, which just means that in Planck units, the charge is bigger than the mass. That's true about the proton to 19 orders of magnitude. So that's not surprising, but it means that this shell can't live by itself. Without the interior geometry, there would be a horizon much larger than the shell itself. So there are no static solutions where there's just a shell and no singularity inside, but these appear to be static solutions where there's a shell and an interior which looks like Reisner-Nordstrom as well. So where does that mass go? We can think about it as all that extra mass being canceled by a negative binding energy in the interior. This is a toy model of what could be happening at the inner horizon, but it's a statement that even in normal classical physics, taking a limiting case of Planck densities, you can construct a macroscopic shell that's Planckian, that's at the scale of quantum gravity, and yet is macroscopic and can describe an alternative to the Cauchy horizon. All of that is simply to say that it is possible in GR to create very large shells and match to interior metrics in which the density of the shell is Planckian, but the exterior mass is much smaller than you would have measured the local mass of the shell to be. And that bodes well for the possibility of asking, could a shell exist where we think an empty horizon exists for the Schwarzschild metric? We do the same story. We say there's an exterior metric, which is just Schwarzschild, and we take a shell. But this time we put the shell just outside of that horizon, and we slowly bring the shell towards the Schwarzschild horizon. And we can ask, are there static solutions instead of a shell falling in? Are there static solutions where the shell sits there, there's, say, singularity in the center, and the density of the shell approaches M Planck? The shell then, outside the shell will be Schwarzschild. Inside the shell, it's spherically symmetric. We will again take the Reisner-Nordstrom metric on the interior, and we do that by having a singularity with charge, and the shell will have the opposite charge to cancel the charge on the outside and give us Schwarzschild. We don't need an exact cancellation for this. You could have slightly different charges to repeat this exercise for an exterior charged black hole. I'll just focus on the Schwarzschild. It's the same as before. We use junction conditions to match, and we can ask questions about the shell. Is it reasonable? Can it have positive mass? Can it satisfy null energy condition or dominant energy condition? Is it reasonable matter-wise? It's the same exercise. There's a metric inside and outside. They look Schwarzschildian. They have function in front of dt squared and 1 over the function in front of dr squared. A trivial rescaling of the t coordinate for the inner geometry allows us to use r and t as global coordinates. And the functions fi and fo are letting you know where the horizons of the inner geometry or the horizons of the outer geometry are. The difference is here, the shell is outside the horizon of the Schwarzschild metric, and it's going to be inside all of the horizons of the inner Reisner-Nordstrom metric, which means none of the horizons are physical. This will now simply be a shell, a singularity in the center, no horizons, and we will ask, can we take that shell and approach within a Planck length of the horizon? We do that by matching, again, the two metrics on either side, inside and outside, and we can find the density and pressure and charge of the shell. And we'll parameterize the location of a shell as the Schwarzschild radius times 1 plus epsilon. If we go through the same math, we find that the density again tends to a constant in the limit that epsilon goes to 0, but that the pressure again diverges as 1 over the square root of epsilon. So we use the same procedure. We ask what happens if we put the shell just a Planck length, physical Planck length, what would be a physical Planck length away from the horizon, using the metric on the exterior. That sets the value of epsilon, and from that we will get a pressure, and it turns out when you're a Planck length away from the horizon, your pressure is also Planckian. Again, we want reasonable matter, so we want the density to be at least the value of the pressure, and so we choose our remaining interior parameters, R1 and R2, which are essentially the charge and the mass of the interior singularity, and by doing so we can get a density which is Planckian. The density for these values are positive, and so the shell mass and pressure in this case are positive, so it appears to be a reasonable matter that can match these two solutions. And then we can ask some of the physical characteristics of this region in the interior. Again, we find that when the shell is a Planckian distance away from where the Schwarzschild horizon would be, then the curvature throughout the entire interior of the black hole is Planckian. The curvature everywhere in this macroscopic space. And if we ask a physical question about the distance from the shell to the origin, r equals 0, it's again a Planck length. So again, macroscopic size, but if we were taking the geometry seriously, if we would have believed GR in the interior, in this limiting case, the distance between r equals 0 and our shell is a Planck length. That means for any black hole that ends up in this configuration with a shell at the horizon as opposed to a vacuum at the horizon, the volume of the interior, and therefore what you think of as the entropy of the system, should scale like the area instead of the volume, which is sort of a natural desire of black hole thermodynamics. And this is a very simple physical geometric reason why this would be the case. We have worked, and when I say we, Surjeet and I, and the real hero, Ryan McManus and Emmanuel Berti, worked out the radial stability of such a shell. It turns out to be stable for a large region of rhos and p's, equations of state, but I will not discuss it here. What I will simply say is we have a stable solution which is static and is therefore a new kind of naked singularity. And what we'd like to ask is, can we relate this to an actual physical black hole? How would something like this form? Necessarily, the formation would violate general relativity, as Surjeet said, but we will make some plausibility arguments about why it would be reasonable to think something like this could form. There are naked singularity solutions out there solving equations of GR. They're extremal Kerr and Reister-Nordstrom metrics, where the horizons cancel each other effectively. There are fuzzballs or gravistars or sufficiently large, low density blobs, essentially. Of course, sufficiently large, low density clouds of matter can collapse into black holes. And so one could ask, how could a low density blob evolve from a black hole where there's vacuum at the horizon to something where there is non-trivial physical stuff at the horizon? And as Surjeet said, we feel that it is morally reasonable to violate general relativity where densities and curvatures are Planckian. And that, during the formation period, we would say is only really in the tiny region around r equals 0. And so one can ask, how could that system evolve to something which is macroscopic in a way that violates general relativity, but is low density. And we feel that a more compelling story is perhaps that it is high density. And we've made the argument that a high density surface could be macroscopic in size and still allow for a reasonable mass, or the correct mass, black hole in the exterior. So this is the core argument of why we're interested in solutions with Planck density shells at the horizon, distinct from things like gravastars and fuzzballs. Let's hark back to something we all know about, which is the formation of neutron stars. Neutron stars form by, again, matter which is collapsing. It cannot be held up by non-gravitational forces and collapses until it hits something at very high densities. We might describe the collapsing matter as either gas of atoms or ionized plasma, and it will have characteristics associated with those laws. When it collapses, you can ask, what does it end up as? But the only way you would be able to predict what it would end up as is if you knew some nuclear theory. You knew that what happens at 10 kilometers, or where densities of 200 MeV to the fourth are attained, is when you've reached densities where a different set of laws, a different Hamiltonian, becomes important. And so the physics of the interior of a neutron star is very different because it involves a different set of laws that only become important at QCD densities. And so we'll just ask the same question about black hole evolution. You have a blob of matter and it is collapsing. Gravity now wins over whatever forces and pressure is keeping it apart. Those densities will collapse past what we would call the horizon scale of the Schwarzschild geometry, and you would hit Planck densities. And the question is then, what happens next? And I would submit that there are two possibilities. One is that that blob at the center grows back out, and the other possibility is that it doesn't. And the it doesn't possibility is the thing that's been tracked and believed and followed and assumed for the history of black holes. But you can ask a very simple question, is if we don't know what the Hamiltonian is that tells you what time evolution does, past that point where you get to Planckian densities, how do you know? I would suggest there's a 50-50 chance that it stays still or that it grows back out. And in fact, the staying still version has a paradox due to the Hawking information problem. So at least it is worth a look to see if descriptions of the evolution of a black hole beyond the point of Planckian densities could be described by something that comes back out. Little chat things come up, but I don't know how to get the chat while I'm in the keynote mode. So you can unmute yourself and just ask the question. That's okay too. So collapsing matter, which hits Planckian densities and then evolves back out, we can ask how large of a region can be at high density. As we saw, you can have solutions, ours perhaps as a toy solution, where you have Planck density shells at the surface, and the negative binding energy seems to cancel the total energy density in that system to allow for much smaller masses asymptotically. This aspect is just a known aspect of gravity, of general relativity. Inflation allows for violations of energy conservation or different values of local energy. And inflation is, in a sense, perhaps describing what's happened at the inner horizon, which is mass inflation. And firewalls could be just simply another example of a system which evolves from something at very small scales at high densities to something at very large scales, and Planckian in nature, but positive and negative energy densities mostly canceling. You could worry about the statement that Surjeet said, which is that, well, wait a minute, if you go into the black hole, you're going in a positive time direction. If anything comes out of the black hole, you are going in a negative time direction. Are there going to be some causality issues associated with something moving back out since you're moving back in time? Here's the crustal coordinates. And if you had an infalling shell, you would layer this on top of those coordinates. And the green part then will have its own metric associated with a blob of matter. Will not be the black hole geometry, but it will pass in through the horizon and to the singularity. And this infalling matter follows the trajectories associated with GR, because the matter and the density, until you get to the singularity, is low, is much lower than in Planck. And so we trust GR to describe the dynamics of the system, GR and whatever pressures associated with the interparticle dynamics. Once you hit the singularity, you've hit a Planckian density, and you can ask, well, can't I now just evolve back out? Let's say you evolve a shell, a blob, back out until you get to the horizon. You can if you are dramatically violating general relativity. And the interior of this region dramatically violates general relativity. So the surface of the shell has no reason to treat this system as geometric. There's just gravitational forces and the interior forces with respect to the dynamics of super-Planckian stuff. And even though in the Schwarzschild language or the sort of coordinate language of geometry that we're taking a space-like trajectory, there is no violation of causality. And you can prove that this shell, even if it almost took a negative null surface as a direction to get out, there are no kill your grandmother type scenarios that one can generate in this system. It's because the background is not Lorentz invariant. There's a rest frame. And so one has to check for every system. For this system, stuff can come back out. And the nominal nature of us calling it geometry is lost when half of the space, you shouldn't even believe GR anyway. You violated the equivalence principle. And so really it's then a statement about forces. So the ultraviolet requirements that we need for that singularity and the growth is that it allows what we would think of as space-like evolution. There is some cancellation between internal mass and binding energy in that region so that we have Planckian physics, but the exterior mass remains low. And we think this is plausible because we've been able to come up with a existence proof of a solution in the limit from GR. And similar cancellations like this must occur in Reister-Nordstrom type geometries. The other thing we would like to have happen to explain, and this is something we're thinking about and working on, is to explain why such an expansion should stop at the horizon. I won't discuss it here, but we can discuss it offline. Just a quick comment about experimental signatures and other implications. The signatures of firewalls are associated with what a naked singularity would be. There would be deviations from the no-hair theorem, and we would hope anything that's exploring the near horizon geometry of the black hole could see sources of other fields, either mass moments, dipole, quadrupole, higher moments, say quadrupole and higher gravitationally, or other fields that are sourced by the surface. We think that the ring down of the quasi-normal modes would be set by firewall physics. Perhaps they're masked, perhaps a delay of a firewall coming out after a black hole merger would not then affect the quasi-normal modes, but a glitch might occur at some time a little bit after the formation of the final black hole, something that you would hope to be measurable at LIGO and perhaps soon. And then the properties of the surface, like reflectivity with respect to electromagnetism or even gravitational waves, that could be something seen mapped out in templates at LIGO or in radio astronomy, very low frequency radio astronomy for solar mass or 10 solar mass black holes, but in principle, possible signals. Now the caveat is we don't know what the formation time is. to solve the Hawking information paradox, we'd say it has to be less than the page time, which is longer than the age of the universe. But there's nothing in the dynamics associated with this system that suggests those sort of timescales. That comes out of a limit of asking about the information paradox and not about the dynamics of the evolution of a Planckian system in the interior. So it could be of order a timescale RS, the light travel time across a distance, which would be a Schwarzschild radius. One note, these are weird light states. They have very large internal mass and negative binding energy, which appear to cancel. This is something that happens in quantum field theory with Goldstone bosons, say pions or neutral pions where quark masses are zero. Those masses are zero, even though the kinetic energy of the quarks inside of the pion are of order of the QCD scale. The binding energy perfectly cancels it. This is ensured by symmetry in Goldstone's theorem. We have no symmetry reason for a cancellation in the firewall solutions, but weird sort of surfaces, or at least expectations of surfaces, come from causality in GR. There are vacuum energy calculations which regulate surfaces in rotating BTZ black holes, inside of which you get closed time-like curves. Those come from quantum calculations of the vacuum energy and divergences at the surface. We know that there should be a similar divergence at the inner horizon of a Kerr and Reissner-Nordstrom black hole at macroscopic scales, again tied to causality. There, a Cauchy horizon where you lose predictivity. And there's a similar causality problem associated with the outer horizon of a Schwarzschild black hole. It just takes much longer to get to, and it's quantum mechanical in nature, the Hawking paradox. Nevertheless, there's something important causally about that surface, and perhaps there's something about causality and the association of forces, not thinking about geometry, just about physical forces, that allows for large cancellations between positive and negative contributions. Now, the super speculative slide and just other statements to conclude. Firewall and naked singularity solutions could mean a lot about black holes that we don't normally assume. First of all, that black holes don't actually evaporate. In fact, if you take the surface and you put it at Planckian temperature, you find far outside of the black hole, you get radiation of order of the Hawking temperature. But any temperature lower than that, you get much less radiation. And an ice-cold surface would produce zero radiation. Global symmetries may actually be preserved under quantum gravity. Here we have some evolution that turns into some surface. The black hole object is some messy, very dense thing like a neutron star with many degrees of freedom, with entropy sort of stored and shown out there on the surface. Perhaps global symmetries are good symmetries in the ultraviolet theory. If we can't use black holes and internal black holes to make statements against them. Black hole hair could destroy things like superradiant growth of light fields. People have tried to put constraints on axions from detecting and measuring and potentially accurately measuring eventually rotation or high spin black holes. But if the black hole itself has some non-trivial surface, it can mix states and destroy this growth. So bounds like that would go away. It weakens limits on black hole evaporation for, say, primordial black holes, or LHC limits on extra dimensions and black holes produced at colliders if they don't radiate. And then you could imagine potentially there's a gauge theory analog of firewall solutions, another way of generating light states, which is not associated necessarily with Goldstone theorem and symmetries of that. One of us suggests that perhaps there are new solutions to the hierarchy problem associated with such things. And I will end there. Thanks.
Thank you, David. Are there any questions?
David, I wonder about this black hole evaporation. I'm Arkady Weinstein. If imagine that it would be possible to observe this Hawking radiation, right? and particular spectrum or whatever, then it could be the way of checking what you are saying, or my understanding is wrong.
Yeah, I mean, if there could be a system where we'd be lucky enough to be able to actually measure Hawking radiation, that's a very direct check on this system. And unfortunately, Hawking radiation is both very low frequency, it's in radio, but the intensity of it is extremely low, of course, as well. If we could produce something like a black hole at the LHC, so you'd need a few other lucky things, large extra dimensions, low Planck scales, things like that, then potentially one could see those sorts of things.
Okay, thank you.
That we would even say that, you know, if there are all these limits that people place on primordial black hole dark matter based on Hawking evaporation, right? Like if they're less than some mass, you think they're evaporated too quickly to have caused a background of, I don't know, like X-rays or whatnot. So we would say that it's actually very reasonable that that's not the right story because we can't actually solve the black hole information problem. So perhaps what you end up getting are, in fact, objects that could have been hot at some point, but not quite as hot as Hawking, and just become remnants that are, like, you know, heavy, 10 to the 16 grams or whatnot. So for all we know, there might be primordial black holes that are sort of in the so-called ruled out window because it may just be that Hawking evaporation is not the full story. I think there's a question from Elisa about, like, how do you expect the glitch associated to the firewall formation to be in gravitational waveform modeling? This is actually a great question because, in a sense, you know, you would see these LIGO guys come out every now and then and say that they have, you know, tested GR and whatnot. But the way we think this process happens is that when two black holes merge, you actually first do form the regular horizon, because when the black holes are, just as they're coming in, the regular horizon will in fact form, okay, because nothing magical is going on in our story. And so the beginning of the horizon formation, the prediction should be exactly what GR tells you it should be. There is in fact no deviation expected at that point. But then at some point, which we hope would be short, but in principle could be very long, we do in fact expect the firewall to get out. So there would be, as you're saying, a glitch that would appear, but that would then be delayed in time. Okay, the exact time scale could be as short as RS times some log factor. That's typically what you might expect. But in principle, it could be as long as page time, in which case we would be host. We have no way of living that long. But if it is something that is RS times log something, then you would see this essentially as additional power in the gravitational wave signal with a delay. So once instruments get, so right now, I don't think the instruments are quite there to be able to see small amounts of power, but if there is in the future, as the signal to noise does get better, if something is speaking out of the signal, you should be able to see it.
Yeah, hi. So can I ask a question? So did I understand correctly that you have a two-stage evolution, so that if very shortly after formation of the black hole, I will find the Schwarzschild horizon, so I will find nothing on the horizon if I go there, and then at some later point I will find this shell of matter.
Yes.
Yeah, that must be the case, because during the infall, you never reach Planckian densities. You're very low compared to Planckian densities. So all evolution inward must track general relativity. It only must be when the density surpasses the Planck scale can the thing evolve back out. And so there is a time scale there, but it could be very short. It could be, like Surjeet was saying, of order RS. So just the light travel time across RS times some log factor because of a log divergence with time close to the horizon.
And then you said if you're motivated by information, so by correct information processing, then you might also take this time scale to be pages time.
Yes. So we would say that, you know, if as long in principle, right, that the information needs to get out only at the page time. So it might be that this shell takes a long time to get out. So I can't logically require the shell to get out shorter than the page time. So at that point, it's only a hope. But as David was saying, it's a reasonable hope in the sense that all the dynamics tied to it don't really know anything about information, page, nothing, right? It's just like some Planckian evolution. And in the case of the inner horizon, you know it has to be quick. because otherwise your host there. So it's not unreasonable that it is fast.
And so if it were fast, so let's say much shorter than pages time, would you say information comes out after this shorter time scale? So once this shell of matter has formed, then you will start deliver information?
Yeah, that's right. Because after that, the shell is out, there's no horizon anymore. So whatever comes out, comes out.
Yeah, in a sense, it's already out. The shell is just outside of the horizon, and therefore it's contained in any aberrations within the physical object itself. And if you counted what you think this entropy would be, and you divided up the shell into Planck mass little bits, then again, the number of states that you would expect roughly produces an entropy that you would expect. We don't have a coefficient because we don't know what the actual UV, quantum gravity theory is, but at least in terms of counting, it's about right. And all the information is there and in principle can be probed directly.
Okay, great, thank you.
And to some extent, I can even share what it is that perhaps motivates us, right? Is the fact that, like, as we were saying, when in the traditional picture of a black hole collapsing, there is no doubt that you will get to a point where general relativity breaks down, right? Nobody can argue about that. Beyond that, what the solution becomes is just a bet. Does it remain as what GR predicts, which is a possibility, or does it become something totally different? The black hole information problem suggests that it is very reasonable that something very different happens. If something very different, and if something has to get out, you have to break GR, you have to be at Planck density, there is no option about that. Then you are led to this interesting question that thing can then have signatures in that you actually form, this firewall-like thing. And today we live in a time where something like LIGO can actually physically probe this. So I never had ever thought, if you'd asked me this 5 years ago, would it be possible for you to see Planck scale physics in your lifetime? I would have laughed it off, right? Come on. But now it seems to me that arguing this way, there is a reasonable chance that we might in fact learn about Planck scale physics from LIGO. And that is something that 10 years ago, I would have laughed at that comment, and maybe I've gone crazy now that I think is reasonable, but you can see the argument. I can't assign zero probability to that.
Okay. Are there any other questions? If not, let's thank Surjeet and David. It was a great talk. Thank you.
Thanks, everybody.
Thank you very much.
Thank you. Thank you also to you, Guido.
Thank you.
Yes.